Hi, my name is Aman Arora, and this is a presentation for our paper titled Tensor Slices to the Rescue, Supercharging ML Acceleration on FPGAs. My co-authors are Samidh, Dr. Vaughn Betz, and Dr. Lizy John. Here is an agenda of our talk. In the beginning, I'll introduce the proposal, which is adding tensor slices to FPGAs, and look at reasons as to why we are adding them. Then we'll look into the architecture of the tensor slices. Then we'll see how we evaluated adding tensor slices to the FPGAs. Then we'll look at the various results as to how adding tensor slices impacts the metrics like area and frequency. Then we'll look at some related work, and then we will conclude. So let's get started. Machine learning and deep learning have revolutionized our life. There are ML and DL applications around us every day. Hardware acceleration for these applications is commonplace because of the compute-intensive nature of these applications. The alternatives range from highly flexible CPUs to highly efficient ASICs. FPGAs are very interesting in this space because they provide the parallelism that these applications require, and they are also very flexible, which is very important in the changing world of ML and DL. FPGAs have traditionally had logic blocks, DSP slices, and RAMs in their resource mix. This is what makes them very flexible, but also this is what reduces the performance we can get for ML and DL applications from FPGAs. So a question naturally arises, can we improve the performance of FPGAs for ML and DL? To answer that question, we propose adding tensor slices to the FPGA resource mix. A tensor slice is to machine learning just like a DSP slice is to digital signal processing. Tensor or matrix operations are at the heart of ML and DL, and a tensor slice supports all of these common matrix operations. On the right picture, these blue blocks are tensor slices, which have been added to the resource mix of the FPGA. So why add tensor slices? There are several pros of adding tensor slices, the most important one being compute density. Now we can pack more compute in the same area footprint of the FPGA. Tensor slices are coarse-grained and have less degrees of freedom, which leads to faster compilation, which is a big advantage, especially looking into the future for FPGAs. These also reduce area and power to implement ML hardware and also lead to faster frequencies, as we will see later in the results section. Adding tensor slices can lead to better out-of-the-box performance for ML and DL as well. There are some cons. For example, adding tensor slices leads to more heterogeneity in the FPGA, which means the tools become harder, but the cost is transparent to the end users. Then we can say that these slices make the FPGA slightly less generic or flexible than a typical FPGA today, but we think it is worth it because there are so many applications of ML, and ML specialized families of FPGAs could be created. So let's now look at the architecture of tensor slices. Here is a high-level diagram of the tensor slice. The tensor slice interacts with global routing on the FPGA using connection box and switch box, just like other blocks do. It has a local input crossbar, which has been added to alleviate the routability problems with a large block like tensor slice, which has many IOs on it. The core of the tensor slice consists of 16 processing elements and some control logic. The control logic is split into three parts. The first one is the input logic, which basically reads data from the RAMs and sends the data to tensor slice processing elements. And then output logic reads the outputs from the processing elements and sends it out. And then we have muxing logic, which muxes between the various modes that the tensor slice supports. The tensor slice supports two modes, tensor mode and individual PE mode. In tensor mode, the tensor slice performs matrix operations. There are three submodes here: matrix multiplication, element-wise addition subtraction, and element-wise multiplication. These are common operations in neural networks these days. Matrix multiplication is used in fully connected layers, convolution layers, recurrent layers. Element-wise add and subtract is used in normalization layers, for example. Element-wise multiplication is used in dropout layers, for example. The individual PE mode is where the tensor slice operates on scalar operands. There are three submodes here: multiplication, addition, subtraction, and MAC. In each of these modes, there are two precisions that are supported, int8 and FP16, which is IEEE half precision. And these modes are selectable dynamically. Let's talk about the tensor mode in a little bit more detail. In the tensor mode in FP16 precision, the tensor slice acts on 4x4 matrix operands and generates a 4x4 matrix result. But in int8 precision, it acts on 8x8 matrix operands and generates an 8x8 matrix result. This is done to utilize the IOs or ports fully in each precision, and we know ports are pretty costly. Also, we observed that there was a lot of hardware sharing between these two precisions for these two sizes. The most compute-intensive operation supported by tensor slice in tensor mode is matrix multiplication. For this, we use a systolic architecture. The first input matrix moves from left to right. The second input matrix moves from top to bottom, and the result is calculated during the shifting process and is shifted out towards the end in a column-wise manner. We also support chaining of tensor slices. By doing that, you can perform operations, matrix operations on larger matrix sizes. The individual PE mode has been added to reduce the impact of adding tensor slices on non-ML applications by improving utilization. We fracture the slice such that the inputs and outputs of individual PEs are now exposed, and each PE can now basically be used as a mini DSP slice. It's not a full DSP slice because it has reduced functionality. It can be used as either an adder or a multiplier or a MAC. Because of pin limitations, only 12 out of 16 PEs can be exposed. We did not add additional ports just to support individual PE mode. It should be noted that the delay to get to the individual PEs or to use the individual PEs is higher than using a DSP slice or a logic block based adder or multiplier or MAC because of the local input crossbar. This slide shows the internals of the processing element in FP16 mode and int8 mode. In int8 mode, the tensor slice processes 8x8 matrices and needs 64 logical PEs. And for that, one physical PE is split into 4 logical PEs, thereby creating 64 logical PEs out of 16 PEs. Okay, finally, the operation of the tensor slice. The inputs are expected to be populated in RAMs. Then the addresses, strides, and mask inputs of the tensor slice are configured. Then a start signal is asserted, after which the tensor slice reads the input matrices from the RAM. Data flows into the tensor slice and compute happens. And then the tensor slice writes output matrix into a RAM and then asserts a done signal. This diagram on the right is showing a high-level block diagram of the inputs and outputs of the tensor slice. There are more details of the tensor slice in the paper that can be referred to later. Let's now look at how we evaluated our architecture. The goals of evaluation were threefold. First, to compare the performance of a modern FPGA with an FPGA containing tensor slices for ML applications. Secondly, to evaluate the impact of adding tensor slices to FPGAs for non-ML applications. And third, to study the sensitivity of various metrics to the percentage of FPGA area consumed by tensor slices. We used many tools for our evaluation, the most important ones being VTR and Coffee. VTR is an academic tool from University of Toronto for our FPGA architecture exploration. It takes in an FPGA architecture description file and a Verilog design and performs synthesis, placement, and routing on that design for that FPGA and generates area timing reports. We also used Coffee, which is another tool from the University of Toronto. It is a transistor sizing and modeling tool for FPGAs. It takes in the properties of an FPGA architecture, performs spice simulations, and generates area and delays for the various FPGA subcircuits. We used another feature of Coffee where it can take the RTL definitions of hard blocks like tensor slices or DSP slices and take them through a standard cell flow before feeding them into the logic to update the area and delays of the overall tiles for the FPGA. The areas and delays obtained from Coffee were put into the architecture files that were fed into VTR. We implemented a DSP slice similar to Intel Agilex-like. It supports all the major modes and precisions, except for bfloat 16. We did not support that in the Tensor Slice either. The delays of our DSP slice implementation came out to be similar to Agilex, not the same, as slightly lower. And our DSP slice spans 4 rows in the FPGA layout. We implemented the Tensor Slice based on the architecture that was described earlier. The critical path of the core of the Tensor Slice was shorter than the DSP slice because it has fewer modes. But because of the large number of inputs it has a larger crossbar, and therefore the overall delay was larger and the frequency was slower. The Tensor Slice spans 8 rows in our FPGA layout. On the right side, the table shows the area of various components of the Tensor Slice. We can see that about 28% of the area is routing, which is less than the percentage on the DSP slice. The Tensor Slice has a higher logic to routing ratio than a DSP slice. This slide shows the various parameters of the FPGA, like wire segment length, the flexibility of various blocks, the layout, etc. These are similar to Intel Stratix 10 and Agilex FPGAs. The baseline FPGA that we used was an approximation of Intel Agilex architecture. We used the same resource mix as AGF027 in terms of the percentage of area and percentage of count of various blocks. On the FPGA with Tensor Slices, which is the proposed FPGA, we created 3 variations with different area spent on Tensor Slices. 3% of the total area of the FPGA fabric spent on Tensor Slices, 6% spent on Tensor Slices, and 9%. The different percentages basically resulted in different number of columns of Tensor Slices in that proposed FPGA. The table here shows the relative area of various blocks on the FPGA fabric and the number of blocks and hence the number of columns for each type of block in the baseline and the 3 proposed variations. Benchmarks. For non-ML applications, we use the 7 largest designs from the VTR benchmark suite. Because that suite does not have any ML and DL application-based designs today, we created our own. The largest design in our benchmarks for ML and DL was a TPU-like design. Then we had some fully connected layers, a convolution layer, and a couple of element-wise layers as well. Okay, let's look at some results now. Compute throughput. In in-date mode, the Tensor Slice has 15x compute throughput compared to a DSP slice. In FP16 mode, it has 7.7x compute throughput compared to a DSP slice. It is important to note that although the compute throughput of the Tensor Slice is higher, it does have a utilization-related limitation. The effective compute throughput can be lower when the problem size does not evenly divide into the dimensions of the Tensor Slice. For example, if we are performing a 7x7 matrix multiplication, then 15 out of 64 PEs will be wasted. This is in in-date mode. Let's look at resource usage now. For non-ML designs, the resource usage did not change between the baseline and the proposed FPGAs. That's because no Tensor Slices were used. But in ML designs, Tensor Slices were used instead of DSP slices in these designs. And we also saw a significant reduction in logic block usage in these designs as well. Let's look at the area results. The area consumed by a design on an FPGA is equal to the logic area plus the routing area consumed. For ML benchmarks, we saw a significant reduction in area. The chart on the left shows for each ML design how much area was used relative to the baseline, and we can see that on average the area used was 0.4x. For non-ML benchmarks, there was no change in the area, and that is because the logic area does not change because the resource usage remained the same as we saw on the last slide. The routing area does change a little bit, but our model was approximate and did not capture those changes. Let's now look at how frequency was impacted by adding tensor slices to the FPGA. For ML benchmarks, we saw an average speedup of 2.4x. That was because the paths across the various blocks in the FPGA in the baseline case were now absorbed inside the tensor slice. The achieved frequency for these ML benchmarks was not sensitive to changing the area consumed by tensor slices as well. For non-ML benchmarks, we saw an average degradation of about 1%, which is very low. That was because of the increase in routing wire length, because now tensor slices are in the way of routing. And as the area consumed by tensor slices increased, there was slightly more degradation that was observed. Let's look at the last set of results, which are the impact of adding tensor slices on interconnect. The tensor slice has a large I/O footprint, which can reduce the routability of the FPGA, and adding a local input crossbar alleviates that significantly. For ML benchmarks, we saw a significant reduction in routing wire length, which is shown in these bars in this chart here. As the area consumed by tensor slice increases, routing wire length reduces in benchmarks where tensor slices were chained. For non-ML benchmarks, there was an average 1% increase in the routing wire length, which is also not significant. A large number of tensor slices in the FPGA can cause a significant increase in the routing wire length and may even lead to insufficient resources for non-ML designs. Okay, let's look at some related work. Both industry and academia have proposed and deployed improvements to FPGAs for ML in the recent years. Intel supports flexible integration of heterogeneous tiles in system in package in their Agilex FPGAs. Xilinx Versal ACAPs add AI engines. Acronix and FlexLogix have also added ML-specific blocks on the FPGAs. In the academia, adding shadow multipliers to logic blocks has been proposed. Enhancing DSP slices for lower precision multiplications. Also has been proposed is the addition of register files in DSP slices for data reuse. Intel recently announced the Stratix 10NX range of FPGAs, which add a block called Tensor block on the FPGA, which is similar to adding tensor slices. Very little information is known about the tensor blocks yet, but there is a presentation in this conference about that, so we'll get to know more. But this block is also tuned for matrix, vector, and matrix multiplications, just like the tensor slice. Okay, let's conclude the discussion now. So in summary, we proposed adding tensor slices to FPGAs to reduce the gap between ASIC and FPGAs for ML and DL applications. We saw the benefits that we can get by adding tensor slices on FPGAs for ML applications, and we also saw that adding tensor slices does not significantly impact the FPGAs for non-ML applications. With the abundance of ML and DL applications, we think that adding tensor slices to the FPGAs is an attractive proposition. While this research has shown promising results, there is still some more work to do. We are working on adding matrix vector multiplication to the tensor slice. We are adding, moving the RAM interface outside of the slice. We are adding other precisions like B416. And we're also adding other benchmarks to our evaluation, including full neural networks. Thank you everyone for listening. We also want to thank our reviewers for their insightful feedback that helped us improve the paper significantly. Thank you.